Sir, we can't hear you.
Okay. Yeah. Now I hope I'm audible. Yeah. Good evening, everyone.
Yes, sir.
Okay. So last time we discussed the preparation of alcohols by reduction. NaBH4 is a mild reducing agent. That's what we discussed. I think we were here only.
Yes, sir.
Ketones can be reduced, and they are hydrate donors. Okay, they give H1. So NaBH4 can reduce aldehyde, it can reduce ketones, and it can reduce acid chlorides. But NaBH4 being a weak reducing agent can't reduce carboxylic acid or its rest of the derivative except RCOCO. It can't reduce ester, it can't reduce anhydrides, okay, and amides. They are not being reduced. So you can see that NaBH4 is helping us to get alcohols from aldehyde and ketones. On the other hand, LiLH4 is a strong reducing agent as compared to NaBH4. It is a strong reducing agent. So what's the mechanism for LiLH4? They are all considered to be hydride donors. Okay. Aluminium is actually trivalent. We know that. So aluminium should be AlH3, but you have one H minus extra. Got it? So this H minus is going to come and join itself to the carbon because this is H minus. Why? How come we know that it is H minus? Because aluminium is minus, it has got extra H minus, and the carbon can make only 4 bonds, so one bond need to be pushed up. So you get this H minus being added to this CO. So you will end up with 1H being added, O minus, Li plus. Then the next step, you do the hydrolysis. Suppose if I would have taken D2O. D2O means D plus and OD minus. Got it? So the D plus is going to come and join on the O minus. So you are going to get OD, and on the carbon you are having H. Got it? So this is how we are going to get. NaBH4 can also reduce. Suppose if I give you NaBD4, instead of hydrogen I have taken its isotope NaBD4 followed by NaBD4, then you take H2O. So this is D minus. Okay, this D minus is going to come and join itself to the carbon of the C double bond. Okay, this is D, and O minus is going to come, will be neutralized by the water, OH. So I hope this is clear which isotope to be connected. So whosoever is with the NaBH4 or LiLH4, that is minus, that is hydride, that will be joined to the carbon atom, and the H plus on the oxygen is going to come from the water, or D plus if you have taken D2O, that is D plus which is going to come on the oxygen, right? So these are very important reducing agents, very important. And LAH being a strong reducing agent can reduce. So LH, this is quite easy. Reduction by LiLH4 of hydrolyzed product of an esters give. Okay. Esters have two parts, we know. So we are going to get two alcohols. Look here. So first H minus is going to come in, and this is going to form O minus. But as I told you that double bond O is very stable, so it is going to form double bond O again, and this OCH3 is being replaced. So you are going to get an aldehyde first, but the reaction is not going to stop because you have four hydrides. Okay, so this aldehyde will be reduced further, more H minus will come in, and it will reduce further until you get an alcohol. So this bond is going to get cleaved. You are putting H, then you are putting more H, so you are going to end up with alcohol, and this methoxide came out, and that also gave an alcohol. So with if you carry out the reduction of esters, you end up with two alcohols. I hope this is clear to everyone. All carboxylic acid derivatives will give you alcohols except amide with LH. Carboxylic acid is there, RCOCl is there, RCOOCO, this is anhydride. Ester, amide, aldehyde, ketone, you have LH, whose full form is lithium aluminum hydride, LiAlH4, and SBH, sodium borohydride, which is NaBH4. So LH being strong, it will reduce. Sodium borohydride will not reduce. It will reduce, and SBH can reduce RCOCl because it is most reactive among all. LAH can reduce. SBH cannot reduce this. LH can reduce this. SBH cannot reduce this. LH can reduce this. Sodium borohydride cannot reduce this. Aldehydes can be reduced by both. Ketones can be reduced by both. Got it? And what are the products? From all of these, you get alcohols as the product of reduction. From these two also you get alcohols. From aldehyde you get primary alcohol. From ketone you get secondary alcohol because you have two alkyl groups. For amide, from amide, you get RCH2NH2. This thing you should note. Got it? So just keep this in mind. So if you want to get amine, you need to start with amide and LAH. Okay, let's do this. So what is going to be the answer to this problem? You have CH3Br, you took KCN. and then you hydrolyze the KCN with, you got B. The B is reacted with LiLH4. You got C. Got it? So what is going to be the final answer? It is going to be an ethyl alcohol. Okay, let me do it quickly. This is cyanide. First reaction is SN2, Br is going to come out. You are going to do the CH3Cl. H3O plus, you will hydrolyze it completely. H plus is going to come on the nitrogen and OH is going to come on the carbon. So you will have a carboxylic acid. And ammonia will come out. Ammonia as ammonium. So we don't bother about ammonia because it is an inorganic product. Then you reduce LiLH4 it by LiLH4, so you are going to get an alcohol. So that's how you are going to get the product. Got it? Just one more thing. Suppose if you take this molecule, let's do one more question. Got it? What product you are going to get if you react it with LiAlH4? And what product you are going to get if you get NaBH4? So LH being a strong reducing agent can reduce both. This is ketone and this is ester. As you can see, this is cyclic ester. So in esters, this bond will get cleaved upon addition of hydrogen. So what you are going to get? OH. Okay. This will become OH, and this, because the ring will open up, so this O will not go anywhere, it will become OH. Got it? With NaBH4, only the ketone is going to get reduced, the ester is going to remain as it is. So that should be the answer. Okay. Now we come to the aromatic alcohol. Aromatic alcohol are phenol, they are prepared by Dow's process. So first you need to get chlorobenzene. Okay. Chlorobenzene can be prepared by reacting with chlorine, but not in the presence of light. Be careful. Light we use for alkanes. Okay, if you have alkanes, then you use chlorine and light. You use chlorine and FeCl3. So you get chlorobenzene. This chlorobenzene, you aqueous NaOH and NaOH at a very high temperature, you can see. It requires very high temperature because it is partially double bond character. So it requires very high temperature to overcome this electron cloud and OH will join itself. So you require 300 atmospheres, 628. This is Dow's process. This is nucleophilic aromatic substitution or bimolecular NAS. Bimolecular NAS. If you have NO2 group, so you can note down the temperature, that is very high temperature. It is 350 degrees Celsius. So aqueous NaOH, it is not going to be possible with aqueous NaOH. Suppose if I take this kind of substrate, one Cl is being directly connected to benzene ring, another Cl is being connected to aliphatic group. Then aqueous KOH or aqueous NaOH, that is going to react only with this, but not with this. Got it? Because this requires, this one is aromatic halide. It requires a very high temperature. But that is aliphatic halide. That can easily, because this is not a double bond character, pure single bond. It can react very easily quickly. So you can see here OH minus is there. OH minus, this is the mechanism. It pushes, it comes and joins itself to the carbon atom bearing the chlorine. It pushes the pi bond. It pushes the pi bond, you get the minus charge. The minus charge actually circulates. So if it circulates, this NO2 is helping the minus charge to get stabilized because NO2 is present at the para position. So this can come at NO2 also. So this is actually decreasing the energy and increasing the reactivity of the chlorobenzene. But the group need to be at the ortho and para position. Then only it can happen. Got it? So then what happens? You need to get back to the aromatic ring complete with complete 3 bonds. So this minus is going to come again and it will eject this chloride ion, and you are going to get this. Got it? This is going to be an easy step, fast step, because you are the aromatic character is being resumed. Okay. Yes. And if you have more and more NO2 at the ortho para positions, the reaction is going to become more and more easier. As you can see here, you just react with water and you just warm it. Why it is so reactive? Because this NO2 is doing the resonance, and it is bringing in positive charge at its ortho and para positions. There is one more NO2, this one, that is also bring positive charge to its respective ortho and para positions. There is a third NO2 group, this one, that is also bringing in the positive charge. So this whole of this positive charge actually is increasing the positive charge on the carbon atom bearing the chlorine. So it becomes so positive that even the water molecules can react with it by simply warming. So here you are not requiring high temperature as you were seeing here. Okay, in the above cases, just you warm it with water and you get the product. Okay. Yeah, so how to prepare? Let me summarize it quickly. How to prepare phenol by Dawes process, which is nucleophilic aromatic substitution, in which you react chlorobenzene with NaOH. Okay, that's the process. But that's not aqueous NaOH. It is at a very high temperature and pressure. As you can see, the temperature and pressure are very high for normal chlorobenzene, 620 T and 300 atmosphere. Sometimes you get, it is written in 2 steps. Actually, you have a basic medium, so you are not going to get phenol because you get phenoxide ion. and then you react it with water to get OH. This is House process. So this is one way of preparing phenol. But if you have ortho and para positions, if you have electron withdrawing groups, then the speed of the reaction is going to become more and more, and you will not be requiring high temperature and pressure. Okay. The other method for the preparation of phenol from benzene is by sulfonic acid, through sulfonic acid. The above method was through chlorobenzene. So first you need to get the sulfonic acid by sulfonation of benzene. So benzene you can do the sulfonation by reacting it with concentrated H2SO4 or just simply sulfur trioxide. You can use concentrated H2SO4 or sulfur trioxide. So you get benzene sulfonic acid, or you can use oleum also. Oleum is actually H2S2O7, which has SO3 mixed in H2SO4. You get benzene sulfonic acid. You heat it strongly in the presence of NaOH. So same biomolecular NaS occurs and SO3H is replaced by OH. Then because it is basic medium, so you will get ONS, so you require H plus in the next step to make it OH. Got it? The other method is via diazonium. Diazonium we take the advantage of the good leaving group of good leaving character of N2. So first you need to make diazonium. Diazonium, you know, how can you make the diazonium? So if somebody asks you to start from benzene, then it is also very easy. So from benzene, you can do the nitration by taking nitric acid in the presence of H2SO4. So remember, if you take simply H2SO4, you get sulfonation, benzene sulfonic acid. But if you take nitric acid and H2SO4, okay, you are going to get nitrobenzene. Nitrobenzene you are going to reduce. How you are going to reduce it? SnHCl or FeHCl. You are going to get NH2. That is aniline. Aniline you react with NaNO2 plus HCl. Between 0 to 5 degrees. So that will convert the NH2 to N2 plus. And now N2 plus being a good leaving group, it will come out. You cannot stop it. Upon heating, it will come out. And you can put the nucleophile or the group of your requirement in the place of N2 plus. So because we are dealing with the preparation of phenol, you need to react the aromatic diazonium salt with dilute H2SO4. So in dilute H2SO4, who is the attacking substance? The water. Or you can just put water also. That is also will work. Dilute H2SO4 means it contains water which acts as a nucleophile. N2 comes out upon heating. It is SN1 reaction, and H2O comes and occupies the position on which the N2 was present. Got it? So through diazonium. Next method for the preparation of phenol is a very famous reaction, that is cumene hydroperoxide method for the preparation of phenol. So let me explain it. What is cumene? First of all, cumene is isopropyl benzene. On benzene, you have isopropyl group, as you can see. Look here. You have an isopropyl group. 3 carbon, normal propyl means all 3 are connected up one after another. If it is connected from the middle carbon, it is isopropyl, right? Then, and how can you get this cumene or isopropyl benzene? That also is very easy. You can start with, there are many methods. You can start with propene, and you can take H plus. For H plus, you can take H3PO4, or you can take H2SO4. So H plus, but don't take HCl or HI, because if you take HCl or HI, they will come and join on the double bond. This H plus is going to, these are a strong acid, but their anion are not going to come in. So once you have H plus here, to get this cation, you react, you mix it with the benzene. So this cation participate in reaction with benzene through EAS mechanism, and you get this. Or there is one more way. You can take isopropyl chloride along with AlCl3. AlCl3, you know, is a Lewis acid. It will abstract the Cl minus, cation will form, and benzene. Got it? So here also you can get it. So now once you have cumene, you oxidize the cumene with oxygen in the presence of light or heat. Okay. Oxygen is a biradical species. You must have read it in your MO theory. And this hydrogen is most reactive because the radical which is formed at this position, this carbon atom, which is benzylic position, can undergo resonance. So you have this OO radical being connected to this position, and then you have H. This is known as cumene hydroperoxide. This is peroxide. On one side you have cumene, and on another side you have hydrogen. So cumene hydroperoxide. And that's why the name of the reaction, cumene hydroperoxide method, for the preparation of love. Now what you do is you heat it strongly with acid. Okay. H2SO4, you heat it. So with H2SO4, what happens is this get protonated, and we know that in H2SO4, the OH get protonated and it comes out as water. So this OH get protonated, it comes out as water, and you have positive charge being generated on oxygen, and there is a migration of phenyl as, because it is just like a carbocation. So whenever you have a carbocation, it can the neighboring groups can shift onto the carbocation, leading to the formation of a new carbocation, which is going to be more stable than the previous one. Okay, so this can get shifted. Benzene is more easy to shift. So you are going to have this CH3 CH3. Benzene, because it is shifted, I'm writing it as phenyl. Okay, and now we are left with a carbocation on carbon, but a cation on carbon, right? And now you have water, because you have taken acid in aqueous medium. Now you have water. Okay, so the water actually joins it. Okay, and you get this CH3, CH3 OPH NOH, and this is unstable. There are two oxygen on one carbon. It is unstable. So what you get, this OPH comes out, H plus comes out, and you end up with acetone and phenol. That's how it happens. So the question can be asked. Okay, the question can be asked not only from the standard part, but side reactions and details can also be asked. Got it? So let's do this quickly. The structure of intermediate A in the following reaction. So we discussed everything. So you already started with cumene and you reacted with the oxygen. The intermediate A is none other than the name of the reaction itself, which is cumene hydroperoxide. The oxygen will get added to this carbon, OOH. So this is going to be the answer. Very simple question. Okay. Next question. Just try it quickly. In this question, they have not provided us with the cumene. Instead, they have started with the benzene. Okay. So benzene, you need to react with, you need to do the alkylation of benzene. And for alkylation, the reaction took normal propyl chloride. You can notice this is normal propyl chloride, not the isopropyl chloride, because in iso the Cl is connected in the middle. And then you have anhydrous AlCl3, which is the catalyst of Friedel-Crafts reaction. This is Friedel-Crafts reaction. So Cl is going to come out, that is sure. By AlCl3, which is a Lewis acid catalyst. Cation is going to form, and cation always have a tendency to shift if it is becoming more stable. So the cation is being formed as primary, but it is going to come over here because it is secondary. Always do check for the rearrangement of carbocation before proceeding for the final product. So this is wrong. This option is also wrong because here you made the cation on the position where Cl was connected, but you have not carried out the rearrangement. So the cation is there, cation is going to shift inside. We're going to get a secondary cation, and that secondary cation is going to come and join in. So these two options could be the answer. And you ended up with cumene. Got it? Then you reacted this cumene with oxygen. So OOH, that will give you cumene hydroperoxide, and you heated it with acid. That cumene hydroperoxide breaks further to phenol and acetone. Normally, we forget the side product of phenol. Everybody remember that phenol is being generated because it is the name. It is in the name, cumene hydroperoxide method for the preparation of phenol. But everybody forgets the side product. The side product is acetone. There are many questions which are being asked on the side product. that it is acetone, so do remember it. And many students forget. So everybody remember the cumene hydroperoxide method give phenols, okay, but what is the side product? That is acetone, so do remember it. So this is there, and so answer is going to be this one. This is just a straightforward reaction. Question is being asked, just only simple thing. The simple error we can make over here is that we forgot to carry, if we forgot to carry out the rearrangement, then our question is going to go wrong. Now, acidic strength of alcohols. Alcohols are slightly acidic, but not. They are somewhat close to. Their acidic strength is close to that of water, or less than that of water, more precisely. Because the hydrogen is connected to electronegative atom, oxygen, so it can get ionized. And lesser the pK, more will be the acidic strength. So here you can see the different acid being compared. HCl, acetic acid, methanol and water are very close. Look, alcohol and water are very close to one another. Got it? In the range of 15. Now, if you have different type of alcohol, you can compare their acidic strength. Okay. As the H plus is removed, you are left with alkoxide ion. This is alcohol. And this is alkoxide ion. So you are left with alkoxide ion. This is minus. And if you have, this is alkyl group, this will exert plus I effect, which makes this alkoxide ion unstable. Okay. Alkyl group is electron donating, and it is O minus already has a negative charge. This R is pushing more and more electron toward the oxygen. It is becoming more and more negative, so and not going towards the stability. So it is becoming unstable, and it will reduce the acidic strength of alcohol, because if it is unstable, then why our alcohol will get ionized? So what I mean to say over here is, the more or the bigger the alkyl group, more will be its inductive effect. This is primary alcohol, this is secondary alcohol, this is tertiary alcohol, which has inductive effect or plus I effect coming from three sides. It is going to make the O minus more rich in electrons. So if O minus is more negative, then H plus will not be ionized. It is less acidic. So acidic strength of alcohol is like this. This is the acidic strength. pK value is just reverse of acidic strength. It is going to be maximum for tertiary. Look here. The tertiary alcohol it is 18, for isopropyl alcohol 17. So if you have more and more alkyl groups, acidic strength will be less, pK will be more. That is a very simple thing you need to know. I hope it is clear to everyone. Do stop me if you need more explanation if something is not clear. Suppose if I compare the normal alcohol like aliphatic alcohol, which doesn't have a benzene ring, just a normal alkyl, or it could be an open chain or it could be a cyclic, with aromatic alcohol, which is the phenol. So phenol is going to be more acidic than cyclohexanol. Why? What could be the reason? Reason is this: it doesn't lie in the alcohol itself, you need to remove the H plus and you need to make O minus, and O minus you need to check whether it is stable, whether it is getting stabilized by the adjacent group or destabilized. Okay, so here you can see what happens if phenol loses its H plus. You are left with phenoxide ion. This phenoxide ion will undergo resonance, and you have negative charge and I have written the resonance structures coming on this, which was originally on O minus. This you can see it is coming on ortho position, para position, and ortho position. Okay, so what I mean to say over here is this negative charge got dispersed on multiple positions, so it was stabilized. So phenol can lose its H plus more easily than a normal alcohol which cannot undergo resonance. Phenoxide ion, which is formed by removal of H plus from phenol, was stabilized by resonance. Got it? If it is stabilized by resonance, okay, so it can lose its H plus more easily, right? And if you put some groups which can help this or then which can help this negative charge to spread further, then definitely the acidic strength of the phenol is going to increase. If you put electron withdrawing group, but where you need to put the electron withdrawing group, that's a very important question. You need to put the electron withdrawing group at ortho and para positions, because those are the positions from which the negative charge is passing. Okay, so you can see over here, and also you need to keep in mind that the negative charge where it passes through ortho and para position for the reaction, for other type of reaction. This is a very important point. This picture you need to keep always in mind. So acidic strength of phenol, as I told you, if you have electron withdrawing group present at ortho and para positions, the resonance will occur in a better way, and you will have more stability of phenoxide ion. Okay, so you can see in this case, this is meta-nitrophenol or 3-nitrophenol or meta-nitrophenol. This is meta, this is para. Which one is going to be more acidic? Just no need to write these structures in detail because it is a time consuming process. So what you can do is you can put the negative charge at ortho and para position with respect to OH. So that is where, or you can draw the complete structure. Look, it is coming on ortho position, then it is coming on para position, and it is coming on ortho position again. Okay, but you can notice that it is not coming on the position where NO2 was there. But in the lower case para-nitrophenol, the negative charge is actually coming on ortho and para positions, and para position you have NO2, so it can spread further on NO2 also. Look, this I'm talking about this structure in which the negative charge is coming on NO2. So it is becoming more stable by doing more resonance with the NO2 group. So definitely the negative charge, if it gets pulled more by NO2 group, When it is pulled by NO2 group, if the NO2 group is at ortho and para position. So the group at ortho and para position exerts minus R effect. Meta position group at meta position will not exert minus R. Got it? So this, in this case, you can see that this is going to be more acidic. So its pK, if it is more acidic, pK is inversely proportional. It will be having lower pK, and that one is less acidic. That one will have higher pK value. So I hope this is clear to everyone. Okay. Acidic strength of phenol. Now we proceed to the chemical reactions of phenol. In order to know, sorry, excuse me. In order to know where the reaction is going to happen, you need to know the resonance structure of phenol. This thing you should keep in mind. Always you should keep in mind. Either for the phenol or for the phenoxide ion, the lone pair, when it will be delocalized with the benzene ring, you will see the negative charge coming on ortho positions and para positions. So these are the positions where which are more electron dense, which are more rich, which carries electron density. So whatever the reaction you are going to perform on ortho and para positions. I hope this is clear to everyone. Okay. So if you do the nitration, look, what are the products which you are going to get? Orthonitrophenol and paranitrophenol. Got it? You took dilute HNO3, whose reactivity is less. If you took concentrated HNO3, which has more NO2 plus ion concentration, you are going to end up with trinitrophenol. But where the 3 NO2 are going to come in, you can check over here at all the ortho and para positions. Got it? Because why not at meta? Because meta charge doesn't have the electron density. Ortho and para positions are more rich in electron density. So those are the positions where the electrophile is going to come in and where the reaction is going to happen. If you use dilute, you will just have one NO2 group attached either at ortho or at para. If you use concentrated, reaction will proceed by more extent, and you have 3 NO2 group attached at all the 3 ortho and para positions. Okay, so this is nitration of phenol. This is picric acid. There is one very important question, that how you are going to separate these two isomers. Can you tell me how you are going to separate these two isomers? Okay. You are going to separate them by steam distillation. You pass the stream through the mixture of these two isomers. Orthonitrophenol has lower boiling point. Paranitrophenol is having higher boiling point. So it can come out with the steam. So this is steam volatile. Why they are having lower boiling point? Due to intramolecular hydrogen bonding. This molecule doesn't react with its neighbors. The hydrogen forms hydrogen bond with the O minus of NO2 because they are quite near to each other. NO2 is present at the ortho position. This is due to intramolecular H bonding. This is there in the NCERT also. But what about the para-nitrophenol? Para-nitrophenol, OH and NO2 are far apart. They are not close to one another, as you can see. So OH group and NO2 group being very far from each other. No intramolecular within the molecule, the hydrogen bonding doesn't take place. That is not possible. It takes place between different molecules. That is intermolecular hydrogen bonding. Got the point? So intermolecular hydrogen bonding and all the molecules are tightly held. They are joining each other. They are holding each other by hydrogen bonding. So this actually has more or higher boiling point. Got it? Let's talk about some other type of reaction. This is halogenation of phenol. Halogenation means you are putting the bromine, chlorine. Mostly it is chlorine and bromine. You don't react it with F because fluorine is actually very less reactive. Okay, it is very less reactive fluorine, so you don't react it with F. You react with Cl or Br. Iodine also you don't react because iodine is reversible. Okay, so that is called halogenation reaction. As you can see here, halogenation is basically attaching bromine or chlorine, mainly bromine or chlorine to benzene ring, and how you are going to do it. This is a very important question, but very simple also. You need to add bromine, and you add it in the presence of a solvent which is carbon disulfide non-polar. The other way is to take bromine in water, which is polar. This is non-polar. Because it is non-polar, so phenol will not ionize. You cannot have this. No phenoxide ion is formed. You just have phenol. Phenol also undergoes resonance, the lone pair of oxygen, but the extent of resonance is less because oxygen is neutral, and if it participates in resonance, there is a charge separation. Got it? So you have plus and minus, but the minus charge is less on ortho and para positions, and plus charge will be there on the oxygen. If you put it in water, water being a polar solvent, it will let the phenol ionize itself because it has acidic hydrogen. You know that. So phenol will get ionized to phenoxide ion NH plus. And as you know, this phenoxide ion, this is O minus now, and it will also undergo resonance just like phenol, but the negative charge is going to be higher on these positions. Got the point? It is going to be higher. So if it is going to be higher, the reaction will be more. Okay, and you are going to get tribromo derivative. This is the white PPT. This is also the test for phenol. Got it? You put bromine water, you get a white PPT with phenol, but in phenol, and you got only one product because you have bromine connected to all the three positions. Okay. And if you put bromine in carbon disulfide, you will have just two products because only one bromine will get connected, not two or not three. Because if phenol doesn't ionize, it will be rich but not as rich as phenoxide ion at ortho and para positions. The negative charge will be lesser. So Br, only one Br, it can react only with one Br2 molecule. So either at ortho or at para. It is same like a nitration. If we used dilute HNO3, only one NO2 was attached either at ortho or para. If we use concentrated HNO3, at all the three positions NO2 were attached, all ortho and para position, you ended up with picric acid. But in this case, you are changing the solvent, that is letting the phenol to ionize or not to ionize. So with that, actually, it is changing.